Hello everyone, and welcome to our MEC 569 presentation for our fixed-wing practical project. The main objective of this project was to fly a fixed-wing UAV glider through a narrowing corridor and have it land in the designated region past the narrowest point. To accomplish this, we had to make use of an ultrasonic sensor to have the UAV avoid the wall and then prove this via video evidence of a successful trial. As you can see from the diagram, the wall distance starts out at around 10 feet and reduces to 1.5 feet at the end, and the total distance is about 15 feet.
Now into our strategy and system design. Looking at our airframe, we designed our fuselage in a way to ensure that the CG is as far forward of the UAV as possible to ensure that it is forward of the quarter-inch core to allow for static pitch stability. This was done by making the fuselage thickest in width towards the nose of the plane and thinnest at the end. With this, we have ample room to mount the majority of electronics at the nose of the plane to bring the CG as forward as possible. Additionally, a long slot was created for the wing mount and allowed for easier adjustment of the CG after already mounting the electronics onto it. Moreover, on the wings, dihedral rings provided roll stability in our UAV, and the place of them being low was to allow for the least amount of drag as possible. Getting into our algorithm, a ultrasonic sensor was placed on the right side of the plane as it is closest to the side of the incoming wall, and the other sensor was placed on the bottom of the fuselage to monitor the distance to the ground. If the right side sensor reads a distance within about 60 centimeters of the wall, the rudder is moved to as left as possible to make a left turn and avoid the obstacle. For the ground sensor, once it sees a distance greater than 20 centimeters, which would be as soon as it left the launch trail, basically, it would move the elevator up to pitch the plane up, which would give it enough lift in order to make the full distance of the flight. Finally, in our code, a median filter was implemented with a bubble sort algorithm to filter sensor readings. The code works by taking the middle value of every 5 readings, which were sorted in order by the bubble sort, which would more often lead to a correct distance sentence in the end. The reason we have this is from test flights, where we noticed a lot of noise was triggering false readings in our sensors, which this algorithm helps reduce significantly once it was implemented.
For our flight test planned, we first verified the sensor and servo movement, as well as the Arduino and power systems. After confirming everything was working properly, we moved on to flight tests. We managed to get 3 successful trials, in which the drone made it through the corridor while sensing and avoiding the wall. In addition, we also had one failure in which the launch string pulled the ladder to the ground, destroying the rudder and elevator. Here's a video of the event.
3, 2, 1. Okay. This is our flight demonstration. At first, it will be at full speed, and then I'll go frame by frame to show that the UAV detected the wall, and then because of the detection, it was able to avoid the wall. So one thing to note, after it took off, the elevator moved up when it detected a distance change, which increased the lift, pitching the plane up, which made sure it was able to reach the launch pad. So as you see right here, it goes up. Show using here. And I will start with now the outline of the wings, showing where it was going. So at this point, the rudder is completely straight and the rudder is 90 degrees. So we make a line from the wing. It goes up till here. We could say this is the projected path of the plane. If we play it, see it follows that direction, follows that direction, follows that direction. But now the rudder begins to turn. If you look here, it's slightly turned. It's maybe 10, 20 degrees at most. And if we keep going ahead, we see that now it's fully turned. At this point, it is fully turned and the direction is still following the projected path. So from here on out, if we move a little forward, keep going, now it begins to turn. So this is a new line. Next, it turns a little more. So this is another line. And then it continues to turn a little more. So we can add a line here as well. And it just barely misses the wall over here. So in this location, it just barely missed the wall. And once it passes the wall, it keeps go swerving to the left, and it gets caught in the net and basically hits the wall nose first. And it's also past the plus sign marked at the end, so it made it to the end as well. And that is all. Thank you.